in the manufacturing of isobutane from isomerization of n-Butane is to compress the feed stream of n-Butane. It is fed into the compressor at 9.47 bar and 80 degrees Celsius, optimally exists at 18.9 bar and 120 degrees Celsius, so that it can be fed into the isomerization reactor. The work supplied to the compressor is 2100 joules per mole. Calculate the heat that needs to be supplied into the unit per moles of n-Butane that passes through. Let us solve the problem here. Before starting the problem, let us write the given data as per the problem statement. It is a compression process. Let me plot the graph figure. Let us visualize the data in the visualized form. Here, as per the problem statement, P1 and T1 are given. So P1, let me take P1 equal to 9.47 bar. Then T1 equal to 80 degree Celsius. Then they are given P2 P2 equal to 18.9 bar and T2 equal to 120 degree Celsius. And it is a compressor. They given the work supplied to the compressor is W equal to 2100 joule per mole. And since it is open system, let us take the first law of thermodynamics, where we are assuming change in kinetic energy as well as the potential energy is equal to 0. Therefore, the first law of thermodynamics will give us del H equal to W plus Q, small q. That is, I'll be writing here. So, del H change in enthalpy equal to Q plus W. And as per the problem statement, they given W, and the question is, I want to find what is the heat supplied to the system. Therefore, Q equal to del H minus W. That is the formula we have from the open system first law thermodynamics. And if I know what is change in enthalpy during the process, we can find Q since the W is given in the problem. But the difficult part is the gas is highly compressed, where I can't assume it is an ideal gas since it is a high pressure system. I can't assume ideal gas behavior. Okay. Now let me, since it is a single component system, and let me assume it is a single phase system also, as per the Gibbs phase rule, we need two intensity property to define a system. According to me, let me assume in this case, my enthalpy, this enthalpy is a function of volume and temperature. You can assume also enthalpy is the function of pressure and temperature, or pressure and volume. Whatever way you want to assume, you can assume, but let me choose simplest way, mathematically simplest way to assume it is a function of V and T. Therefore, let me visualize the state 1 and 2 in the PV diagram, VT diagram. and in the y-axis let me have V, and in x-axis I have temperature. Let me have my state 1 is here, state 1 here, and state 2 here. Since it is a process of compression, the volume will decrease also during the compression. There is a possibility of rise in temperature. Therefore, the temperature rises, the volume decreases. So this is my state. Let me choose a different color so that we can differentiate the path. Okay. Now I want to find this change in enthalpy. For that, we know that enthalpy can be determined by using the basic formula del H equal to Cp dt. From temperature T1 to T2. If I have the Cp data in terms of temperature, I can determine the H value. For that, let us look at the appendix A.2, which I have here. We have provided the data for the different component. Our case is in the problem statement they given us n butane. Now let me look at the data for the n butane. Let me zoom it here. Yeah, n butane. The value of A 1.935. Value of B is 36.915, and C is 36.915 multiplied by 10 power minus 3, and the value of C minus 11.945 multiplied by 10 power minus 6. And there is no value for D and E are given. Let me write the value. So let me write the Cp value here, which I took it from the appendix A.2. So let me write the value here as a given data. So Cp equal to 1.935 plus 36.915 multiplied by 10 power minus 3 T minus 11.402 multiplied by 10 power minus 6 T square. This is my Cp value. Okay. What we can do is directly substitute this Cp value here and integrate. So it is a capital T. And we can integrate to find del H value, and we can find the Q. But actually, we can't take this data directly to here, because if you look at annexure table, this data are applicable only for ideal gas. Okay, this is only applicable for ideal gas. Ideal gas. But as I said earlier, we have system where my gas pressure is highly pressurized, where I can't hold the ideal gas behavior assumption. Therefore, I need to do something else to use this data for my system. But fortunately, we know that enthalpy is a state function, not a point function. So it does not depend on whatever path I take, but it only depends on my initial and final state. That would utilize the available data. I'm going to create hypothetical state which may utilize the Cp data. For that, what I'm going to do is I'm going to expand my gas from state 1 to a hypothetical state here, from here to here, and that is I'm expanding my gas from here to here, and I'm moving my system isochoric process then I'm moving back to my state 2. Almost it should be a, let me write a straight line. So let me have the expansion under isothermal condition. Since I have vertical line, this isothermal condition, then it is isochoric process where volume kept as a constant. And again, I am bringing back to my state 2. Yeah. And this is a hypothetical state. What I'm assuming here is when I am doing my increase in temperature, this happens, this where it behave like a ideal gas. So it is hypothetical state. Step number 1, let me mark the step number 1, step number 2, step number 3. Okay, and let me save this. Step number 1. Step 1 of problem solving. Now let me take this. Let us continue the problem with another empty page. Now further, let me take only this figure. So I took this image here, and here, as per the problem statement, sorry, as per the state property, del H, that is equal to change in enthalpy in the step number 1 plus change in enthalpy in step number 2 plus change in enthalpy in the step number 3. Since enthalpy is a state function, summation of all 3 steps will be my actual change in enthalpy. Okay, since I took my enthalpy is a function of V and T, I can write dH, it is a change in enthalpy in the differential form, is equal to dou H by dou V dV at constant temperature plus dou H divided by dou T at constant volume dt. Okay, so I have written, since enthalpy is dependent property which depends on my volume temperature, I can write in terms of differential form. Now this equation, I have two portions. Okay, in my hypothetical state, I have two kind of steps. Step number 2 and 3, 2 and 3, where temperature is constant. And step number, sorry, not step number 2 and 3, 1 and 3. The step number 2, where my volume is constant. Therefore, for the step number 1 and 3, 1 and 3, I no need to take this term since dt is constant. Therefore, I have dH equal to dou H divided by dou V temperature constant dV. For the step number 2, my volume is constant. Therefore, this term won't appear. Therefore, my dH will be dou H by dou T volume dt. Dou H by dou T at constant volume into dt. So, these two formulas I am going to utilize for 3 different steps to calculate change in total enthalpy. For del H1 and del H3, I am going to use this formula, that is, I will be using this formula. And for del H2, I am going to use this formula to calculate. So I am splitting the steps into 2 steps. Therefore, I can discretize my steps. Okay. Now, next, let us solve this dou H by dou V at constant temperature, and I'm going to integrate with respect to V. Step number 2. So I'll be erasing that. Now, let me take del H, step number 1, sorry, save as step number 3. Step 3. Okay. Now, let me calculate. As we know that we'll be writing the step del H equal to del H step number 1 plus del H 2 plus del H 3. As I said earlier, del H1 and del H3 can be calculated using this equation, that is del H1 R3 is equal to, as I said earlier, should be integration of I'll be writing here. As we know that it is a dou H by dou V at constant temperature into dV. And I want to replace these H value, this term, in terms of either TPV. Okay. Especially I want to replace in terms of V. That's why I can integrate here. Okay. For that, let me use the fundamental property relationship where we know that dH equal to dds plus V dP. Okay. The derivation of fundamental property, the link I'll be sharing in the description. Okay. You can refer that. And what I'll be doing here is I'll just substitute here this fundamental property relationship. So here V1 to V2. It is a not state 1 to state 2. It is a initial to final state. for whatever condition. If it is step number 1, we want to the intermediate state of volume, and T ds plus V dP divided by dou V into dV. Again, I'll be rewriting that. So here T, though here at constant temperature, dou S by dou V at constant temperature plus V dou P by dou V at constant temperature into dV. Now, again, I have dou S with dou V. I need to replace this S in terms of, again, the Maxwell property. For that, I'm going to use the Maxwell relationship, where dou S by Maxwell relationship. Derivation for this also I'll be sharing in the description box. You can refer that video. Dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. Now I'll be replacing this also in terms of the measurable property. Therefore, here del H 1 or 3 is equal to integration, and thus T into dou P by dou T at constant volume plus V dou P by dou V by at constant temperature of T into dV. So here 1 to 2. Now I want to replace this dou P with dou T in terms of V. Therefore, I can integrate the step. For that, let me, since it is high pressure system, let me assume my system follows Letisch-Kwong equation. That is nothing but P equal to RT divided by V minus B minus A divided by T power 1 by 2 V plus V. And here what I will do, this next step is, I want to differentiate this equation with respect to T at constant volume to find this term, and I want to differentiate this term, this equation with respect to volume at constant temperature, and I want to substitute. I'll be doing that in the separate paint. Now, what we want to do here is, I want to find dou P by dou T at constant volume using Letisch-Kwong equation, and also I want to find dou P by dou V at constant temperature using Letisch-Kwong equation. Okay, let me do one by one here. Let me do it the first term here. Okay, let me change the color. So dou P by dou T, I want to differentiate with respect to temperature at constant volume. Okay, volume. So this will differentiate with respect to temperature at constant volume become R divided by P minus P, and here minus A divided by V plus B is a constant multiplied by minus 1 by 2 T power minus 1 by 2 minus 1. You get R divided by B minus B minus into minus plus 1 divided by 2, and we can put A T power 3 by 2 into V V plus P, and therefore dou P by dou T equal to R divided by V minus V plus A divided by 2T power 3 by 2 V plus V. It is under constant volume. Okay. Now one part is done. Similarly, let me do it for this term also. I want to find dou P by dou V. Okay. Now, now let us try with second. Now let us try. Let us differentiate the second term. That is, we want to differentiate with respect to volume at constant temperature. Here, uh, if you want to differentiate this term with respect to V, obviously we know that P equal to R T V minus V power 2 and minus 10 will come. So if you take this term to numerator, minus 1 will come, minus 1 become minus 2 divided by 2 and multiplied by minus 1. And for this term, I have the complexity. I will use U by V method, okay? And I'll be taking this term alone here. That is A1 divided by V plus B alone I will take. I will keep these two terms aside since these are the constant, and these two terms can be written as 1 divided by V square plus VV. Okay, and apply U by V method, and we know that I'll be writing the formula for your reference. If you want to differentiate U by V, differential of U by V, U dash V minus V dash U dash, sorry, dash dash divided by V square. Okay, let me apply it here for this term alone. Here my U is 1. Okay, but look, my U equal to 1 and V equal to V square plus VV. Now U dash is a 1, so 0 multiplied by whatever term, okay, V square plus VB minus, if we differentiate this V square 2V plus V multiplied by 1. U is 1 divided by my V square. So here V square plus VB power 2. This term will be vanishes since I multiply by 0. Therefore, we'll have A divided by T power 1 by 2. This remaining term. This minus minus will become plus. So plus 1 here and multiply by 2V plus B here at the denominator multiplied by V square plus V P power 2. This is nothing but out of dou P by dou V at constant temperature. Okay, so this is the term. So now I need to substitute this term. this term, and also our previous finding, that is dou P by dou T at constant volume, that is equal to R divided by V minus B plus A divided by 2 T power 3 by 2 V into V plus D. These two terms here, these two terms I need to substitute here, this here, and this here. We will get LH for step number 1 or 3. You have to integrate. Okay, integrate from 1 to 2. So let me do these steps. Substitution of these two terms here and simplification in the next slide. Now we need to substitute in the equation which we done it earlier. I'll be rewriting the equation again. That is for step number 1 or 3. I'll be writing this equation, that is equal to integration of T into dou P by dou T V plus V dou P by dou V at constant temperature Tv. Now we have derived these expression, that is dou P by dou T at constant volume and dou P by dou V at constant temperature from the Redlich-Kwong equation. I'll be substituting and I'll be simplifying the equation. That is del H. You know that our equation del H equal to integration T. We have in the 10th term. Okay. And dou P by dou T is R divided by V minus V. Kindly refer the previous slide. A divided by 2T 3 power 3 T power 3 by 2 into V plus V. Then plus this term V, writing it here, minus RT, which we done it in the previous slide, divided by V minus V power 2 plus A 2V plus B divided by T power 1 by 2 V square plus B power 2, and this multiplied by dV, and total square bracket we have this integration part. Here it is. Yeah, sorry, I missed the term. Yeah, dV, and it is a state 1 to 2. And what I'll be doing is I'll be combining individual term. Before that, to make a common denominator for the first term here and here, what I'll be doing is just multiply numerator by V minus V and denominator by V minus V. Therefore, you'll get V minus V whole square. Then, if you multiply this, I'll be doing that term separately. Then I'll be combining entire time. Just look at here. What I'm doing is R V minus R V divided by V minus V power 2. And here I have to multiply by t. Here also I have to multiply by t. And if you just take this term, v, if you cross multiply this here, you will get v t divided by v minus b power 2. So what will happen is we have a common denominator. So we are having like v minus b power 2 and VRT minus will be cancelled out. I'll be having minus RBT. So if we combine these two terms, we'll get minus RBT divided by V minus B squared. Similarly, you can take this term. I'm just removing this term. So I'll be writing here for the first term equal to minus RB. I'll be writing different color so that we can differentiate the main derivation. Yeah. Here, my integration, you should not forget integration. I multiplied, okay, minus B T divided by V minus B power 2. Okay, now I need to focus on this term, that is the second term. So both the term I have A and A is a common term. Only thing is I have to multiply by T. Okay, and let me do that here. Okay, removing this term. I no need of that. What I can do is plus A divided by T power 1 by 2. Let me take common term. Okay. Now remaining time I have to pull together here. Now let us focus on second term, and the both the term we have A and T power 3 by 2. If you multiply T here, here it become 1 by 2. This T will be cancelled out. Get T 1 by 2. Okay. And let me take A T power 1 by 2 as a common term. And let me write remaining term here. Look here. Here 1 divided by 2V V plus P plus in this term we have to cross multiply this V here. We get 2V plus V multiplied by V divided by, let me take V as a common term. So V plus V whole square and this and total dV. Now we need to integrate this equation to find del H. So next slide, let us do the integration part of this. So this minus RBT divided by V minus B power 2 plus A divided by T power 1 by 2, 1 divided by 2V, V plus B plus 2V plus B divided by V plus V multiplied by V plus B power 2 dV. I will do how this can be integrated and let us solve the problem. Let us let us do the integration separately, since integration itself is the biggest part in this problem. I just done it in a separate Canva whiteboard, and this is what we want to integrate. To simplify the process, I'm splitting the entire integration into three. Uh, this one, this one, and this one. Okay, and that's what the first step shows here. Splitting integration into three parts. One, 2, and 3. And let me integrate one by one here. First, let me take this one minus BRT divided by V minus B power 2 dV. And here I'll just work on the fundamental itself. Okay. And I will consider V minus B as U and I have 1 by u square, and we take v minus v equal to u, du will be dv. So this dv will be replaced by du. So integration of 1 by u square, nothing but u minus 2 plus 1 divided by minus 2 plus 1. That's what I've done it here. Okay, and it is finally I'll be ending it with 1 by u minus 1. So already we have minus minus become plus. I'll have where u is nothing but v minus b, b rt divided by v minus v. Okay, that is the one part is done. It is simplest manner. Now let me take second part. Second part here I will take only the term. I will keep a by t power 1 by 2 as a constant, and 1 divided by 2v plus b dv. I will do the partial fraction decomposition. What I've done is I'm splitting up this equation 1 divided by 2v plus b equal to a divided by 2v plus b divided by 2v plus b. And I'm multiplying both sides by 2v plus v plus b. Then this equation will become like this. And in this equation, we have to substitute v equal to 0. We get a equal to 1 by b. Similarly, in this equation, I have to give v equal to minus b. We will get b equal to minus 1 by b. Then back substitution of a and b value here, I'll get 1 divided by 2v divided by b plus b, that is equal to a value is the 1 by b, b value is the minus 1 by b. So I took b as a constant, and here I have under 2 also constant value. So I have 1 divided by 2b, 1 divided by v minus 1 divided by b plus b. Don't worry, I'll be adding this white bolding in the description box. Okay. And I have this equation. Integration of 1 by b is the ln b, no, that's what I've written here. And integration of v plus b is the minus ln v plus b. And this ln v will have combined ln v divided by v plus b. And we have the constant 1 divided by 2b. That's what I'm having here. So second term is over. Similarly, I will apply for the third term. What is the third term? I have here is the a divided by t power 1 by 2 integration of v into tv plus b divided by v multiplied by v plus b power 2 dv. For that, what I've done just took this integration part from here, just put here the same I took, and I'll be rewriting that. What I'm doing here is I'm just taking this as a constant to avoid the confusion. I'm just keeping aside, and I have 2 v into 2v plus b divided by v square v plus b power 2, and just cross multiply here the v, we have 2v plus b, and this v square will be cancelled out. I have v into v plus b square. Okay, and I'll be doing the partial fraction of this one. 2v plus b divided by v into v plus b power 2. I'll have a divided by v plus b divided by v plus b plus c divided by v plus v square. So similar to here, I just done in different way for the here, and ultimately here I'll be approaching different way while comparing with here, and I'll be here multiplying both the term by the denominator term. Same thing we done it here also. So multiply by v plus b power 2. I just multiplied. I have 2v plus b equal to a multiplied by v plus b power 2 plus bv, v plus b plus cv. And I have to expand since I want to here compare the coefficient of the v values. And I just expanded here, and this is the a plus b whole power 2 square formula. I just expanded here, and I just had it here, and cv. After expanding, I grouped the variable according to the v square, v, and constant. And here the right hand side I have 2v plus b. I'll be here 0 into v square plus 2v plus b. Now I'll be comparing the coefficient with the individual term to find a and b. First, let me compare to the coefficient of v, ab square minus, that is the I'm comparing here, ab squared equal to b. Therefore, my b will be 1 by b, and I'll be comparing b square term so that I can find b equal to minus 1 by b, and v term, that is this term I'm comparing here. After comparing that, I can determine what is the c1 also. C1 equal to 1. Once I determine a, b, and c, I'll go back to the top here, and I'll be substituting what is the A value, B value, C value. That's what I done it here. So I substitute A value 1 divided by B. B value is the minus 1 divided by B. That's what I have minus B here. And C value is the 1. So I have this term. Now I want to integrate integration of V. We know that one ln V. Integration of this ln V plus B. Integration of this will be as we done it the first is minus 1 divided by V plus B. Okay. And we kept this term aside. So now I'm multiplying that term. Therefore, we get A B t power 2 ln V divided by V plus B minus A divided by t power 1 by 2 into V plus B. Now I need to combine all the three term results which we had. I just combined it here. That is the final expression I'm having here. So it is the first term, and it is the second term, and this is the third term. And all other terms are straightforward. If you look at here, this is a straightforward here, and this is also straightforward step. But you may have confusion. I just what I've done is I took ln V plus B as a common term. I'll have A or 2B t power 1 by 2 plus A B t power 1 by 2. Again, I can take the common term. So A 2B t power 1 by 2. Sorry, 2 is not there. Ln V plus B multiplied by here 1 by 2 plus 1, and will become cross multiply here 3 divided by 2. That's what I'm having. 3a 2b power t power 1 by 2 ln v plus b minus 2 t power 1 by 2 v plus b. Now this equation can be used. Okay, this equation can be used to find the entropy change of step 1 or 3. And here is I need to let's not forget, I need to substitute the limit state 1 to state 2, and for that I will explain to you here. Again, I will come back here. What we had is earlier state 1 to state 2. This state 1, this is state 2. And to since the data here we have volume, here we have temperature. Since we don't have CP data for the real gas, we applied hypothetical method where I'm expanding my gas to the lower volume, V low, where my real gas will behave like a ideal gas, and I have heated under isoporic process. Then I brought back to the system to 2. These two are isothermal. That's what we done it in the previous case. And here, the step number 1 and 2, we can apply. We can apply this formula. But thing is, it is a step number initial state. It is a final state. This volume is unknown to me. But what we assume is, I'm just expanding the gas to the maximum volume where the gas behave ideal. Therefore, this volume V intermediate is very high. V large, let me assume almost it tends to infinite. And so now the V1 now, and also I must know the what is the volume. If you want to integrate here, I must know the volume V1 and V intermediate. And V1 I need to determine. I will do it later in the Google Colab, because solving the cubic equation is the biggest task. I just use the programming language to solve that. What I'm going to do is just I'll tell you the intermediate case. Suppose whatever I'm having, let me take this is something else x. After substituting the lower limit, I have minus x something. Okay, and while substituting the upper limit, what will happen is just look at here. V is a very high. It's almost equal to infinite. So 1 divided by infinite, while comparing with the B, V is very high. This term becomes 0, and here also while comparing with V with the B is very high. We become ln V divided by V. So ln 1 we know that it is a 0. So this term also will be eliminated. And also similarly here, while comparing with all other term, V is very high. Whatever value divided by infinite term, it becomes 0. Therefore, all other terms become 0 while substituting for the upper limit. So we no need to worry. We no need to find intermediate volume since we know that is very high. So all the term become 0. Okay, and now I want to find the initial volume and the final volume. So here, while applying for step 1, my lower limit will be V1 and upper limit will be V2. While applying for the step number 3, my lower limit will be my intermediate volume and upper limit will be my V2. So now I need to find V1 and V2 in my formula. Okay, for that I am going to apply the equation which I written the Wenger-Robinson equation here. I just took the values of TC from the textbook Korosky, that is appendix A PC, and from that by knowing the constant of A and B, I just substituted the value of TC and PC. I got A and B, and I defined what is the Lagrange conjugation in the function. Okay, the moment I substituted the I defined the Lagrange conjugation in the function, I can call the function by calling the name Lagrange conjugation. So now again I define what is A, 8 A equal to 8.314. Yeah, we can do it here itself. I'll be substituting here. So I executed the first line. Have then my state 1 condition is the 353.15 Kelvin and P1 as per the problem 9.47 bar. I'm just converting into the Pascal, and low pressure I'm assuming this is a 1 bar. Okay, and I no need of that. I'm not going to use it here. Now I'm using here. Yeah, yeah, I executed first line. Let me check what I've done here. And yeah, here, yeah, I'm not using this low pressure. I'm uncommenting here. Yeah, the moment I know T1 P1 and to solve by any cubic equation or non-linear equation by F solve, I need to give the initial guess. I'm going to take initial guess from the equation of state for the ideal gas. If you look at here, what I've done is here PV is equal to nRT equation to PV is equal to RT. Here I am talking about intensity molar property. Therefore, R multiplied by T1 divided by P1. This will give me initial guess. That's what I mentioned here. I'll be sharing this link also in the description. You can refer. And with that, I'll be get the initial volume of V1 equal to 0.0 0.2588 meter cube per mole. That's what I'll have V1 from Lagrange conjugation 0.02588. Okay, meter cube per mole. Okay, and then similarly, I'm executing for the step number 2 also. Here also no need of low pressure. I'm uncommenting that. I know the temperature and pressure and substituting back and giving the same initial condition, but let me give T2 here. Okay, and I'll get the volume of P1 is I'll be defining here P2. So my volume for state 2 is the V1 0.0. What is a V2? 1274. Okay, that is the volume. This could be written as 2.59 multiplied by 10 power minus 3 meter cube per mole, and this could be written as 1.2 multiplied by 10 power minus 3 meter cube. Once I determine V1, V2, next thing is we need to substitute lower and upper limit here. Lower and upper limit here. Here. For that also I written the code here. Okay, just look at here. I just I split it into two terms. BRT divided by V minus B. V and term 2 I just combine all other term. That is these all the term as I consider term 2, and I written the code, and finally this different del H1 function will combine term 1 term 2. The moment I'm going to give V1 and T1, that will give me back what is the change in enthalpy. So I'll be cutting this, writing here. For me, V1 is already we know that it is a V1 value I defined here. V1 is we defined here. The moment I'm going to give the V1, I'm just calling here this term and followed by this one. V1 is not defined. I'll be defining V1 here also. Yeah. V1 is defined here. Again, let me come back here. Let me check V1 is I'm getting value or not. Yeah. So here I'm getting minus, but I need to convert into plus because first in the equation we have to substitute lower limit. That is the for the first case V1. We need to substitute the upper limit bi. So if you want to substitute upper limit, this entire becomes 0 and lower limit the v1. So minus v1. So I need to convert here opposite here. The del h1 will be my 1367. 1367 1367 0.40 joule per mole. Then we need to go for step number 3 here. Sorry, step number 3. And but in step number 3, we no need to do the unit conversion because uh, here starting initial step will be my intermediate state. Then I'm moving from here to here. V intermediate to the V2. So here, so while substituting V2, we'll get all the values minus while substituting intermediate step. We know that Vi is very large. The entire time becomes 0. Now I'll be just calling the function here again. Only thing is it is my 3, and here I need to give V2 value, V2 and T2, and whatever value I'm getting will be my 3. Okay, and let me execute whether I'm getting error. Yeah, I'm getting V137. Yeah, I'm getting. There is a mistake. Let me check what mistake I made here. Now I need to execute for step number 3. Copy. Just paste that code here. And here I need to do modification here to for that I need to give my V2, so V2 state 2 volume and state 2 temperature, and here let me change 3, sorry, it should be 3 here, okay, because it is the enthalpy change of step number 3, and let me execute here, and we no need to change the cycle since as I said here my initial state is the intermediate state that become 0, okay, and my final state is the my state number 2, so I will be writing this value here, here del H3 equal to minus 2533.72 joule per mole. Now we need to find del H2 to combine all three. Let me first write del H equal to, I need to have this value. Let me take one by one. This value P plus this value let me another thing I need to find del H2. Let me do that here. So now we need to do for step number 2. Step number 1 and step number 3 we have done it. We have calculated the value. Now let me go for the step number 2. And we know that step number 2 is isochoric process where volume remains same here, remain constant. So del H2 we have already took from the previous step. So it is a combination of dou H divided by dou T at constant volume dt. Okay, and from the definition of H we know that H is equal to U plus PV. I'm rewriting this equation, and I'll be getting d of U plus PV divided by dt under constant volume into dt. Okay, and again this equation can be written as du dou U by dou T at constant volume plus, don't forget the integration symbol, dou PV divided by dou T at constant volume dV. And we know that from the basic fundamental property relationship, dou U by dou T under constant volume equal to CV. And since here we are dealing under ideal state, here I no need to use the Rutledge congregation. This term I'll be writing first. This term can be replaced by CV, and I can replace PV as RT. Therefore, plus dou by dou T into RT. Why I'm replacing? Here in step number 2, we are entirely have ideal gas condition, so I can apply the ideal gas equation. Okay, and the constant volume dV. If you differentiate T, you'll get 1. So I have CV plus R, and again from the basic fundamental of property relationship, Cp minus Cv equal to R. Therefore, Cv plus R equal to Cp. Now this equation can be written as Cp sorry, this is dt, not dv, dt. Yeah, dt. Now I can use the equation to find the enthalpy. T1 to T2, and this CP value already we have taken from the textbook. I'll be rewriting that. So this equation can be applied. I'm just removing this. And I know that the final thing, del H2 T1 to T2 Cp dt, and I know that my T1 as per problem statement, it is moves from state 1 to state 2. T1 they given the problem is 3 uh, 353.15 Kelvin. I hope so. T2 will be 393.15 Kelvin. Okay, and just substitution of Cp value R multiplied by 353.15 to 393.15. I will get that is 1.935 plus 36.915 multiplied by 10 power minus 3 into t minus 11.402 multiplied by 10 power minus 6 t power 2 dt. I'll be doing the integration directly here, so I don't want to waste your time. Del H2 will be equal to 8.314 1.935 multiplied by eliminate 393 minus 353 plus 18.458 multiplied by 10 power minus 3, 393 minus 353 power 2, 2 minus 3.801 multiplied by 10 power minus 6, 393, 3 minus 353 power 2. So if you substitute entire value, you will get del H2 approximately close to this value. Be having 496 joule per mole. Now my del H value will be del H1 plus del H2 plus del H3 will be, I know will be using the Python code again, at least for this one, 4696, and then let me execute the code. My del H value will be 3529. So here I'll be getting 3529, let me 3530. Yeah, 4696. Yeah, we'll get approximately 3529 and 6. And once I know the del H value, it is as it is simple that only thing what we asked is, what we expected is find the Q value. Here del H equal to Q plus W, and I want to know Q. That is del H minus W. My del H is 3529 minus my W in the problem given is, I think, 2100. joule per mole. Yeah, 2100 will get del H minus 21. I'll get the answer of work done, that is a heat supply per mole is equal to 1429.67. It is closer to the my exam value. So I'll in the next lecture I'll be solving the same problem but using the departure function. So now we need to do for step number 2. Step number 1 and step number 3 we have done it. We have calculated the value. Now let me go for the step number 2. And we know that step number 2 is isochoric process where volume remains same here, remain constant. So del H2 we have already took from the previous step. So it is a combination of uh, dou H divided by dou T at constant volume dt. Okay, and from the definition of H we know that H is equal to U plus PV. I'm rewriting this equation and I'll be getting a d of U plus PV divided by dt under constant volume into dt. Okay, and again this equation can be written as du dou U by dou T at constant volume plus, don't forget the integration symbol, dou PV divided by dou T at constant volume dV. And we know that from the basic fundamental property relationship, dou U by dou T under constant volume equal to CV. And since here we are dealing under ideal state, here I no need to use the Rutledge conjugation. This term I'll be writing first. This term can be replaced by CV, and I can replace PV as RT. Therefore, plus dou by dou T into RT. Why I'm replacing? Here in step number 2, we are entirely have ideal gas condition, so I can apply the ideal gas equation. Okay, and the constant volume dV. If it differentiate T, will get 1. So I have CV plus R, and again from the basic fundamental of property relationship, Cp minus Cv equal to R. Therefore, Cv plus R equal to Cp. Now this equation can be written as Cp, sorry, this is dt, not dv, dt. Yeah, dt. Now I can use the equation to find the enthalpy. T1 to T2, and this Cp value already we have taken from the textbook. I'll be rewriting that. So this equation can be applied. I'm just removing this. And I know that the final thing del H2 T1 to T2 Cp dt, and I know that my T1 as per the problem statement, it is moves from state 1 to state 2. T1 they given the problem is 3 uh, 353.15 Kelvin. I hope so. T2 will be 393.15 Kelvin. Okay, and just substitution of Cp value R multiplied by 353.15 to 393.15. I will get that is 1.935 plus 36.915 multiplied by 10 power minus 3 into T minus 11.402 multiplied by 10 power minus 6 T power 2 dt. I'll be doing the integration directly here, so I don't want to waste your time. Del H2 will be equal to 8.314 1.935 multiplied by eliminate 393 minus 353 plus 18.458 multiplied by 10 power minus 3 393 minus 353 power 2 2 minus 3.801 multiplied by 10 power minus 6 393 3 minus 353 power 2. So if you substitute entire value, you get del H2 approximately close to this value. We are getting 4 9 4 6 4 6 9 6 joule per mole. Now my del H value will be del H1 plus del H2 plus del H3 will be, I know will be using the Python code again, at least for this one, 4696, and then let me execute the code. My del H value will be 3529. So here I'll be getting 3529, let me 3530. Yeah, 4696. Yeah, we'll get approximately 3529.6. And once I know the del H value, it is absolutely simple. That only thing what we asked is, what we expected is find the Q value. Here del H equal to Q plus W, and I want to know Q. That is del H minus W. My del H is 3529 minus my W in the problem given is, I think, 2100 joule per mole. Yeah, 2100. I'll get del H minus 21. I'll get the answer of work done. That is a heat supply per mole is equal to 14 29.67. It is closer to the my exam value. So I'll in the next lecture I'll be solving the same problem but using the departure function.